So I'm going to pose a question to Rob. Does resistance decrease proportional to the amount of torque you add to a screw? And to do that, Rob, you look like you've brought in the world's fanciest MFT tester and one I've never seen before. Just explain to me what we've got in front of me before we start doing this test.
Right, this is a 4-terminal tester. It's a micro ohm meter.
Okay.
So it just records resistance. It's nothing more than that, but it's more accurate than a digital multimeter. It passes current through the 2 outer terminals, the blue ones here.
Yep.
And it measures the voltage using the small inner terminals there. So we can measure the voltage across a small part or part of the circuit, and it automatically negates the resistance of the leads.
Right.
So by doing it this way, we get a very accurate measurement of the resistance at a point in the circuit and not the whole circuit.
All right, and the points we're going to do is from the front of the screw on the neutral to the conductor behind it, when we add the other lead in, making it the 4th lead, we'll measure the resistive path here, and I've currently set it to 1 Newton meters of torque, so we'll measure its resistance and then we'll start increasing it and see what happens to that resistance. Now we would expect it, wouldn't we, as we get tighter, to probably be a better electrical connection and therefore a lower resistance, but let's see if we can prove that and see what happens when we over torque the terminal as well. So the first one is set to 1 Newton meters of torque. Am I allowed to use your kit?
Yes, you are, yeah.
Okay, so I found a good use for the Wiha torque.
It looks like a bodge, but this is,
torque bar.
It works well.
So we're going to probe onto that, and then we wait a second or two and we get a reading of. So that's a reading there. Just tell me that reading, Rob.
138 microohms.
Okay, so that's the resistance between the conductor and the front of the terminal at 1 Newton meters of torque.
That's right, yeah.
Okay.
Yeah.
Is there a way of working out maybe what that would dissipate in power-wise? Is there a way of coming up with the calculations, how much energy that would dissipate if the terminal was at 1 Newton meters of torque?
Yeah, well, now we've got the resistance reading. Mathematically, it's I squared R.
Yes.
So if we're passing 100 amps, that's squared that's 10,000, multiplied by 138 microohms, gives you about 1.3 watts.
Okay, so that would be, if I left it in that situation with 100 amps running through the circuit, would that cause any issues over a longer period of time?
It would cause moderate heating of the terminal, probably, and I'm not sure, but 1.3 watts could probably be dissipated to the environment without significant temperature rise. Maybe 1 or 2 degrees.
Okay, so
it depends on a number of factors.
Okay, that's all right. So because of the way the enclosures, etc., it will give it a chance to dissipate that heat. Okay, we're going to now set it to 2. So I'm going to bring it up, and we're not going to quite be there yet. So I've gone from 1 Newton meter to 2 next. So I change my bar around so I can get all the way to 2. So we're not at the 2.5 required. So there we go. So we've set that one now with our Wiha torque screwdriver to 2 Newton meters of torque. And I'm just going to bring that terminal back up to the required torque setting of 2. 1 click, no more than 1 needed. And you're going to allow me to do it again, are you?
Yeah.
I'm just going to bring in the bar, and we would expect this to be lower, wouldn't we? I'd expect this to be a smaller number.
Yep.
Position it on like so.
So we had 138 before.
93.
93.
Okay, I think that was me, wasn't it?
Yeah,
you wanted to prod me on the side there and say stand still, didn't you?
Slip of the wrist, yeah.
Yeah, okay. So it has come down. So that makes logical sense, doesn't it? We've got a tighter terminal and we've come down. So that would mean now, under the 100 amp rule you've just gone.
Yeah, it'd be 0.93 watts.
So less. So the problem we might have had, or might not have had, is now obviously less of a problem.
It wouldn't get quite so hot in service.
Okay, so now we're going to set it to 2.5, which is the required torque setting.
And just before anyone asks, when we measure the voltage here using this clever probe, it doesn't matter whether this lead is at that end or that end, because we're actually measuring the volt drop between those 2 points.
Okay. Okay, so there we go, the 1 click. That's slightly tighter now, and that's at 2.5 Newton meters of torque as required. This is what the manufacturer, under their instructions, specify it to be. Oh, wow. That's a big change.
54.
That's almost, let's use easy maths, Gary. It's almost half, isn't it?
Yeah, it is, yeah.
So we're now, the power being dissipated now by that terminal would be almost negligible, would you agree?
Yeah, half a watt or less. Yeah.
Okay, but there's no movement, and we've said in other videos that we've created with you, because your background is being sort of that forensic investigator when everything's gone wrong. Obviously, with a little bit more movement, maybe an under-type terminal, we could see that resistance greatly increasing, generating more effectively heat and causing a problem, isn't it?
Yeah.
Now we're going to take it beyond it. I don't know whether I can get up to 5, so I'm going to go for 4. I'm going to go for 4 Newton meters, and let's see what happens to that reading of 54.6. So go back in with my bar, and again, logic suggests that reading will drop. So we're nearly there. Just whip it round, and there we are at 4. Okay, considerably more than the manufacturer has set it. And let's see what happens to that reading if I can get it to required torque setting. Okay, I'm just going to check that. I know we shouldn't do 2 clicks just to check. Yeah, I'm happy with that one. So there we go. So that's at 4. We bring it back in, just wind it out. We probe on. Let's see how much the resistance has changed now. Okay, near enough. So
58.
So it hasn't made any difference. So that's so tight as better. The more power I put in it, the better the electrical connection. Have we proved that?
It's kind of what we said earlier. You're flattening the conductors. You're getting a bigger contact area up to a point. And once you've achieved that, there's very little gain in increasing that contact pressure.
But what I have done is I've put the screw head under more stress than maybe the manufacturer wants you to, because I've set it at 2.5 newtons. I don't know what's happened to those threads. I've obviously rearranged the conductor pattern in there, haven't I? Yeah. I haven't improved it by any stretch, have I?
No. You may even have taken out some of the springiness of that copper that maintains the pressure.
And you gave a really good analogy before. You talked about a jelly baby, one of my favourite sweets, and you suggested when we got it to a certain springiness, that copper, believe it or not, it springs about, and again, we've mentioned this in the previous video, but once you squash it too hard, the jelly baby being the copper conductors, what's really happening then?
Well, effectively, it's starting to yield, the copper moves and work hardens.
Yeah.
You may get microscopic fractures in that copper.
Right.
You may, for smaller conductors, you may squeeze the copper out from the contact area.
Yeah.
So there's less material carrying the current, and it can actually make things worse.
Okay, and you talked about maybe it going like a cherry red colour, 100 amps over a long period of time, and other factors coming into play, and that's where we start having the really big issues, aren't we?
Yeah, I mean, you can find the resistance with some connectors, and this is an example.
Yeah.
It might increase over time, and if it does increase over time, it can get hot, and the heat can help degrade the connection even more.
Right.
So it becomes cherry red, it can oxidize, it can increase the resistance further, and then you get this runaway situation.
Just give us a brief term on this runaway, just for the people, just that runaway situation. What's happening then, that runaway?
Well, we said here, for example, a loose connection might give you 1 watt.
It does, yeah.
1 or 2 watts dissipated. If that generates heat over time, that resistance might increase. So you might find after a year or 2 service, you might get 2 or 3 watts dissipated.
Because the increase in the resistance.
Yeah, and so as a consequence, it's then running hotter, and it may then start to deteriorate even quicker. That may then develop to 5 or 10 watts, and it will escalate. It will go up as a slope versus time. And when it gets to a certain stage, that heat can't be dissipated, or it leads to a large temperature rise. Cherry red, oxide colour is something that forensic investigators might look for after an event, and that's a clue that the conductor's been running hot for a period of time.
Okay, so when we say forensic investigator, that's at the point that the installation has failed. Obviously there's been an electrical fire. Hopefully no one's perished in the disaster, but we have talked off camera about people that have not survived these events. So we can see there how important it is from all of the stuff that we've looked at that we use the correct kit. So in this case, the Wiha torque screwdriver. We set it to the manufacturer's torque setting because we trust our manufacturer. So they've done all their tests, all their product tests on it, and has said if we go for 2.5 Newton meters of torque in that connection, it links into everything that you do when it isn't that case. They've obviously got that data as well in order that we can be reliable with our electrical connections. And I think that fits in nicely with the stuff that we've done on torque. And again, if torque is the first time you've actually come across it, we've done a CPD on it. I'll leave a link in the description for that as well. Rob, thank you ever so much for all the videos you've done with us in the last couple of days. It's been brilliant. And again, any comments, anything, just leave them below and I'll try and get back to as many as I can. The really difficult ones, Rob, I might have to ring you up.
It's a pleasure.